Next talk is by Dr. Jim Schirber, Pressure Studies of the Yttrium and Strontium Copper Oxide Systems.
Thank you. Well, we've been making purely hydrostatic pressure measurements of the superconducting transition temperature in the lanthanum, strontium, lanthanum, barium, lanthanum systems. And I'm not going to talk about those because I think at this hour of the morning I'll be lucky to get one thought through. So what I'm going to try to do is convince you that we have found a compressibility collapse transition in the yttrium barium copper oxide system. And this work is done in collaboration with Gene Venturini, Jim Kvok, Dave Genley, and Bruno Morrison at Sandia. Now the first thing I got to do is tell you what a compressibility collapse transition is. And it's a kind of transition that occurs in a number of perovskites. And what it amounts to is going from a situation where you have chains of, in this case, oxygen, copper, oxygen, going forever in orthogonal directions, completely lined up, to the situation where you have these chains kinked at the oxygen. And when this happens, when it's kinked, the material is extremely compressible, at least an order of magnitude more compressible than it is when these chains are not kinked, when the bonds are, when everything's just pushing against itself. And the best documented situation for this kind of phase transition is in rhenium trioxide, which a lot of us were involved in studying a few years ago, where we have one of these transitions in the world's simplest perovskite, which is just rhenium oxygen chains going in the three mutually perpendicular directions. And this transition occurs, and we can study it in great detail and see the Fermi surface and the NMR and do the neutron work. Completely documented. There's absolutely no doubt what goes on there. Now, that's as opposed to the system we're going to talk about now, where we really have just an indication this is going on, but I think it's extremely provocative, and I'm convinced that it's happening. This is a measurement of T sub C in the this particular foil is the Chu composition, but we've also done it in the 1, 2, 3 composition. A plot of T sub C versus pressure up to about 10 kilobars or 9 kilobars. And what we have is an enormous increase in T sub C rate of nearly 2 degrees per kilobar, which goes on for about a half a kilobar. And then in our model, the kinks are straightened out, and the material becomes almost totally incompressible, and T sub C only changes less than 1/10 of a degree per kilobar. Hoare et al. Published measurements of T sub C versus pressure where they could scarcely detect any change at all, and that's this quote high pressure above 1 kilobar data. They didn't really get started until after this, so they missed this completely. If we blow this up and look in the first kilobar, we see this is the same data just stretched out, that we have, as I indicated, about 2 degrees per kilobar, and then going to less than 1/10 of a degree. A factor of 30 nearly change in the apparent compressibility. So our picture is that we have this compressibility collapse occurring at a very modest pressure of about 3/10 of a kilobar. And so what's going on in this material is we're sitting right on top of this second order phase transition, with its attendant soft modes and instability, presumably then contributing to the electron-phonon interaction and causing the 90-degree superconductivity in some sense. Thank you.
Thank you, Jim.
Thank you.
Next talk is measurement of the AC Josephson effect from a junction inside a high TC superconductor. John Martinis will give the talk.
Thank you. Before I start, let me mention 3 collaborators that were not in the program: Gaston Collin, Philippe Monod, and Michel Ribault. What we're doing, what I want to describe is possibly the simplest experiment that will be discussed in this conference. What we do is we take a block of high TC superconductor and put it in some sort of copper mount, and then we take a normal metal tip, and with the screw thread we push the metal tip onto our sample, and then we just simply measure the IV characteristics. What we find is something like this. For the strontium and yttrium compounds, these are sort of good characteristics we get maybe after playing with the system for 5 minutes, but no means untypical. These structures, for example, this structure here is very characteristic of a Josephson junction weak link. In this case here, we have a weak link with some shunt resistors. Actually, we have several weak links, and maybe in parallel and in series. Now, we don't know where, well, there's the only superconductor in this circuit is this high TC superconductor. The tip's normal metal, this is normal metal. So these junctions have to be coming from inside the high TC superconductor, presumably near the tip, because that's where the current densities are the highest. Let me note that we don't know whether the junctions are indigenous to the sample or if they're created by stress when we push the tip against the high TC superconductor. Anyway, no matter where these things come from, we can use them to measure or find out some information about this superconductor. So what we do is look for the Josephson effect. Without microwaves, we get an IV structure like this. We put on microwaves, we see steps, quite characteristic of the AC Josephson effect. 5 gigahertz, we see this. What we do is measure the separation in the steps versus frequency. I plotted that in the points right here. And the prediction for H over 2E is given by the green line, and we see excellent agreement. This, of course, says that an order parameter arises from a 2-electron state in this superconductor. We can also sit at a fixed frequency and measure the modulations of this first step, the 0 step, the first step, and the second step. We get some Bessel function behavior that's in quite good agreement with what you would expect from normal weak link behavior. This indicates that a DC Josephson relation, at least close to the sine phi, is obeyed in this system. We've also looked at the temperature dependence. The typical junctions that we get go from 10 nanoamps to 1 microamps. And, well, the IV characteristics just wash out at 6 to 10 Kelvin, and we have no idea why that's happening at this point. For the large critical current junctions, we've seen several of them, but they're sort of uncommon. About a milliamp, we see an IV characteristic like this with some sort of structure here. Presumably, it's some contact resistance in the junction. As you go up in higher temperatures, this is the yttrium compound. This washes out, but we still can sort of resolve it here. If I plot this critical current versus temperature, we have these points. We draw a straight line down to here, and it intersects 90 Kelvin, which is the TC that we get from susceptibility measurements. We can put a magnetic field on the sample, and I plotted here the modulation of the critical current of these steps with applied magnetic field. We see a modulation pattern typical of a quantum interference device. This is sort of a good example. This is sort of a bad example where we see some complicated structure. Sort of the typical modulation field is around 200 Gauss, which is about AC1 in these materials. Very simple microscopic model is that we have superconducting islands that are connected via junctions. Our tip makes contact with one of these islands, and then the current flows into the sample. If magnetic field feeds through one of these squid loops, we get the modulation of the magnetic field. I note this model is consistent with the superconducting glass model of this material proposed by Muller et al. Finally, just to conclude, It's very easy to make junctions in the system. We basically see them every time we cool down. We've seen the AC Josephson effect in the strontium compound at 4.2 Kelvin, and it's a 2-electron state. And, well, we might be seeing some sort of superconducting glass. Thank you.
Thank you very much. The next talk is by Dr. F. Gompf, comparison of the phonon densities of states for superconducting lanthanum strontium copper oxide with the reference compound lanthanum copper oxide.
Okay, thank you. Okay, here's the title again. You don't find it in your paper because the data is so new, you didn't have time to get in it. But I'm glad to show it here anyway. Here's the team that took part. Evert and Renker made the sample. Gehring, myself, Nücker, Reichert, and Renker also are neutron scatterers. Ritschl and Weber are our theory in our group in Karlsruhe. Here shortly the sample as measured inductively measured with a midpoint at 36.1. The whole material was single-phased. The measurements were carried out in a small Millosine reactor where we have a multi-detector time of flight machine in Grenoble. And from the time of flight spectra, we deduce the phonon density of states, which is shown here for the superconductor. We see a very structured spectrum. The spectrum is corrected for multiphonons. And with the help of a Born-von Karman model, which we developed, we can identify the different vibration modes. Put this maybe. Okay. I don't want to go into detail out of time reasons. We focused, of course, very mainly on these high-lying modes. They are oxygen-copper bond bending modes together with the breathing modes, whilst the interplane modes are the high-frequency ones around here, and these are the out-of-plane modes. Those are the ones we wanted to observe and to see if anything strange happened with them temperature-wise or from sample to sample. I may also say shortly that in this Born-von Karman model it was necessary to use very high force constants for the copper O1 coupling constants over 140 dynes per centimeter. Okay, here I compare this room temperature data with the phonon density of states measured for the non-TC sample. What we see, maybe we look at the downer part of the spectrum first. Overall, very much like spectrum. Here at low frequencies, at first astonishing that the non-superconductor seems to be softer, but it's understandable with the tilted octahedra giving rise to such bends, to such rotations or modes. In the upper part, here now we see a shift of these vibrations, whilst here the statistics were very bad on the second run. So we went and looked into it with more accuracy, and the multiphonons were also a bit difficult to correct there. And we took an incoming energy now of above the cutoff of 128 millieV. And measured it at 6K. This is now the superconductor and the high-frequency part measured at 6K. And you see that there is no significant temperature effect for these high-lying modes, interplane or in-plane. The gap here is that's a resolution effect. The resolution is very bad here so far out. So you see it is very much the same. There's no temperature effect to be registered. The middle band of the spectrum, I don't want to display out of time reasons. There is also the middle part of the spectrum from here to here is also, we measured this with 80 millivolt incoming energy, is also very temperature independent. There is, however, a small temperature deviation visible, a softening. Here we compare the first part of the spectrum, now measured with 30 milliV incoming energy, and we see that the superconductor goes soft upon cooling. The 6K there's a slight softening here, registerable. Now I want to compare the high frequency part, superconductor, non-superconductor, both at 6K. And this is the most pronounced effect that we could have measured. One sees that these interplane modes and breathing modes here, the high frequency ones, are shifted, pronouncedly shifted to lower frequencies for the superconductor, just as well as these modes here are shifted to lower frequencies. I want to remember about the talk Schlesinger gave, that he saw at 60 millivolts, this is strong coupling to the electrons, and we see also an effect going from the non-superconductor to the superconductor. So if the bell hasn't rung, I will put the summary up. Okay, via inelastic neutron scattering, we have determined the phonon densities of states for superconducting, for the superconductor and its reference compound, the non-superconductor La2 kappa 04 at 300K and at 6K. Main results, below 10 eV, there's a slight softening of modes for the superconductor. This low TC softening could be caused by soft breathing modes, as Weber has suggested. Secondly, there are two bands of high-frequency mode containing the O breathing modes as well as O kappa bond bending modes. For the high TC sample, the O kappa in-plane vibration center around 85 millieV, the out-of-plane vibrations around 58 millieV. They display no significant T dependence upon cooling. In comparison to the non-TC sample, these two high-frequency bands are pronouncedly shifted to lower energies for the high TC sample, which is also consistent with Weber's calculations.
Thank you. Let me call for one other paper if the speaker is ready. Dr. deLozanne, would you be ready, or shall we have the discussion first?
I could do it now.
Okay, if you could. The title of the talk is Tunneling Measurements on Lanthanum Strontium Copper Oxide by Low Temperature STM.
Make it quick. We're ready to go home. Okay. The new piece of information that I want you to take from this is that the background curvature that we have seen in the various tunneling measurements so far is not necessarily a property of the material, because when we have a cleaved, clean surface, this curvature is gone. So let me show you how we get there. First of all, the people I'm working with are Shuheng Pan, Kokwai Ng at the University of Texas, and the samples were made by Charson and Green at Belcourt. Why STM? Well, 2 months ago, there were no thin films, and so the bulk samples that you have seen in pictures and SEM photographs show a very rough surface and therefore make it very hard to tunnel into. And also with the STM, there's no barrier needed. So we just put these samples into our low temperature tunneling microscope. First thing that we saw were IVs like these. And here I'm showing IVs at two different temperatures, at 12 Kelvin and 77 Kelvin. In this case, the STM is in vacuum, so it's not at 4.2 Kelvin. The sample is lanthanum strontium copper oxide with the right composition for maximum TC. Very sharp transition, 1.1 degrees wide, and an onset of 40 degrees Kelvin. The tip in this case was platinum rhodium. If we take a numerical derivative of the above data, it's easy to see then that you could point your fingers at something that looks like a superconducting gap there. If we let the computer do the work and average IV curves, then much better data is obtained, much smoother. And I should point out that the curve shown here at 77 Kelvin is very characteristic of the material. In this case, we had to dig into the surface of the material because it was as received. Namely, the surface had some crud on it, perhaps some semiconducting or insulating material on the surface. Basically, we never saw a structure like this at 77 Kelvin. So that is a good pointer that gap there is probably due to superconductivity. As I mentioned, if we get a clean surface, the background curvature that everybody's seeing is gone. And in this case, we have cleaved the sample in situ while it's cold in order to not lose oxygen in the vacuum. Again, the temperature is 12 Kelvin. As you can see, the parabolic curvature in the previous data is completely gone. The asymmetry is still there. One might ask, well, why are these curves so washed out? Why don't I have a nice peak and a drop to 0 here and a nice peak on this side? The one thing that is quite different in tunneling microscopy is that it's very common to achieve very high current densities in this type of tunneling. It's very easy to get above 10 to the 6 amps per square centimeter under the tip. In that situation, you can clearly have some depairing, and that can definitely wash out the IV curves. So, getting back to the beginning, our deltas from these curves are 12 plus minus 3 millivolts, 2 delta over KTC of 7 plus minus 2, and the DIDV is shows no background curvature on a clean surface. Thank you.
Thank you very much. See, these papers are open for discussion. Yes, Doug?
Doug Fenimore from the Ames Lab. Dr. Schirber, if you have all these oxygen vacancies, do you really have a good comparison with radium trioxide?
Well, I think that it would probably be at least the analogy would be easier to make in the square planar parts of the material, clearly, but which do in fact in the structures shown tonight show it to be kinked at normal volume to start out with.
Any further questions? Okay, then maybe we should move ahead. Thank you very much. Okay, this I think is the last session. This is our 6 contributions here. So let's start out with the first one, tunneling measurements on lanthanum, strontium, copper oxide. I'm sorry, wrong one. I'm getting confused here. Getting punchy. Far infrared measurement of the energy gap in lanthanum, strontium, copper oxide by D.A. Bonn.
Okay, I'm presenting some infrared optical properties of the strontium lanthanum sample. This work was done in collaboration with Tom Timmis, John Greedon, and Carl Steger at McMaster University, and David Tanner, Mona Doss, and Steve Hare at Florida State University. A relatively small group for this meeting. Just very briefly, to show we have a superconductor, we have a transition temperature at about 40 Kelvin in this material, and it's quite sharp. The blue curve here is in the superconducting state, and the black curve is in the normal state. We don't see the full 100% reflectance that you'd expected in the superconducting state in this material. We take this as a sign that we're seeing a large fraction of normal state material still in the sample. However, when one takes the ratio, one can still get a reasonable idea of what the the energy gap might be in this material. These are two different samples we've measured, and the interesting thing to note here is that we get a somewhat smaller gap for materials that show a larger fraction of superconductor. Now, this is in perhaps linking up with some of the other far infrared work where they see a considerably smaller gap even than this and a much higher percentage of the superconducting effect. Moving up to higher frequencies, the plasma frequency is being measured here, and it's coming in somewhere on the order of 6,500 wave numbers. And some Kramers-Kronig analysis has been done recently, which shows these two large interband structures, one at somewhere around 5,000 wave numbers and one somewhere around 13,000 wave numbers. So briefly in conclusion, we measure the far infrared reflectance as showing an energy gap somewhere on the order of 10 millielectron volts, a plasma frequency of about 6,500 wave numbers, and there are two broad absorption bands at around 5,000 wave numbers and 13,000 wave numbers. Thank you.
Thank you. The next talk is Theoretical Cluster Calculations for Lanthanum Copper Oxide by M. McHenry.
Thank you. What I'm going to tell you about is a molecular orbital basis for high-temperature superconductivity, and I've listed the people who've been working on this lately, but this is basically a model that's been around for a couple of years, which Keith Johnson and Dick Mesmer developed. Let me describe the model to you. Essentially, the model ascribes superconductivity to an electron pair, similar to a Cooper pair wave function, in a singlet state where I show the formula there. Psi plus and psi minus are due to spatially extended layered p-pi bonding or tubular d-delta bonding in molecular orbitals. And these two, the plus and the minus, distinguishes between the phase of this particular orbital. And this particular orbital is an orbital at the Fermi level. Alpha and beta are spin up and down eigenfunctions. We describe this theory describes a binding energy, delta, which is 2EF, 2 times the Fermi energy minus an energy as a function of distance, where the distance parameter d is the distance between these layers or tubes. The E of d is less than twice the Fermi level because of the correlation between spin up and spin down electrons in these layers or tubes, induced by dynamic Jahn-Teller displacements of the atomic nuclei arising from a degeneracy at the Fermi level. This formalism describes a Jahn-Teller coupling parameter, beta, which is related to a displacement, which is related to this parameter d, the electron mass, the ion mass, and atomic orbital overlap at the Fermi energy in the following way. That m over m to the beta goes as delta over d, which goes as the overlap integral. And it's bounded by two quantum mechanical limits in the dynamic effect, one being the harmonic limit at a half, and the other limit being the 0-point vibration at a quarter. And another effect, less than a quarter, one predicts a static distortion, and you can still have coupling between the split states after that distortion. We get a relationship for the TC that's related to two parameters. One, the overlap, and two, this distance parameter. This particular formula reduces to the BCS type formulas in the case of beta being a half, if the Debye frequency can be expressed in this manner, an expression originally proposed by Weisskopf, and if the density of states times the attractive potential can be expressed in that way. These are some examples of TCs calculated from the analysis, and recently we've applied it to these new superconducting materials, where we've used a beta value of about a quarter, indicating that or reflecting the fact that these systems are near a static Jahn-Teller effect. They're near a static type phase transition, and we've used D's, which we get from our molecular orbital calculations, but are rational functions of the lattice constant. Essentially, the D of 2.4 is the distance between oxygen atoms along a 110 direction in the doped lanthanum copper oxide. And maybe surprising, not so surprising, that all you have to do to get 90 degrees is take a square root of 2 type increase in the distance to get this distance parameter to get 90 degrees.
Thank you. I've been asked to just read the titles of the remaining talks. I mean, we'll have the talks too, but just for your information. Superconductivity and polysusceptibility of lanthanum strontium copper oxide under pressure, Meissner effect in yttrium barium copper oxide. Another talk is the Amsterdam-Leiden efforts towards a high temperature superconductor. The third talk is microwave measurements on lanthanum strontium copper oxide. And the final talk will be thermoelectric power measurements on some high temperature superconductors. Okay, the next one is given by Professor Jim Schilling. Superconductivity and polysusceptibility of lanthanum strontium copper oxide under pressure, Meissner effect in yttrium barium copper oxide. Jim?
Thank you. Paul Chu mentioned in his talk that high pressures were important in his finding the higher TC superconductor. He squeezed the lanthanum barium compound at 40 degrees and found that TC went up very rapidly, indicating a potential for higher TC values in this system, or in this complex of systems. Now, the lanthanum strontium system, by the way, this work is done in collaboration with Robert Shelton, Bill McCallum, and Paul Koo of the Ames Labs, who kindly provided us with a sample of lanthanum strontium. Lanthanum strontium's TC value also increases rather rapidly under pressure, approximately 280 millikelvin per kilobar. This is a value similar to that found by the Karlsruhe group and also in Ames. Now, the question would be, why does TC go up so fast? The lambda value increase that you need, if you use a Macmillan formula, to account for this increase that you get at 6 kilobars, so about 1.5 degrees, would be an increase approximately 4 to 8%. All right? Now, lambda would be related to the density of states and other parameters by this well-known formula, so that if the density of states is increasing and is responsible for this increase in lambda, then we would expect to be able to see it if we measure a quantity which is proportional to the density of states, and that would be the polysusceptibility. So we measure the pressure dependence of the polysusceptibility and see if it's comparable with the pressure dependence of lambda. Now, the polysusceptibility looks something like this for this compound. We've seen similar curves before as a function of temperature. It decreases slightly with decreasing temperature. Here you see the superconductivity setting in. This is at about a field of 6 Tesla. We have to subtract off the core of diamagnetism, which is sitting down here, so this difference between the two curves is the polysusceptibility. Now, we've measured both at room temperature and at 70 degrees, so just above TC. The pressure dependence, unable to find any pressure dependence whatsoever in the polysusceptibility to this accuracy. And that means that at a pressure of 6 kilobars, that we observe zero change in the polysusceptibility, that is, in the density of states, plus or minus 1%. And if the density of states increase had led to this lambda, then we would have seen it because this increase would have been 4 to 8%. So the conclusion is that for the pressure dependence of TC, that the density of states does not appear to be the driving factor. And we've heard this before. If you go from the strontium compound to the yttrium barium compounds, the density of states goes down a bit, but TC goes up by a factor of 2. So it doesn't appear to be terribly important. We've also recently succeeded in making our own samples of this same compound, collaboration with some chemists in Munich. This is an example of measurement at 40 Gauss, high-resolution susceptibility measurement versus temperature. One thing that might be interesting here is we observe in some samples a little drop at about 5 degrees above the TC, the Meissner effect, and this doesn't appear when you warm up again. We've seen this in a few samples, and I understand that some X-ray work has also reported similar results. We've also made the yttrium lanthanum compound, which has a Meissner effect setting in about 85 to 90 degrees. We get about 20% of a full Meissner effect at 20 Gauss. This is measured at 140 Gauss. This sample was loosely packed, so we could actually pick out, this is Paul Chu's composition, and Klaus Andreas was able to, in an afternoon, pick out the black pellets from the green material, and using his marvelous contactless resistivity apparatus, where you can measure the resistivity on a milligram sample, he was able to show that the green sample, that's the green dots, which still had a bit of the black material in it, had far less conductivity than the black material. So he proved that the green material is not superconducting, the black material is. We've picked out single crystals of the material. It's in the chemist's four-circle goniometer. We're determining the structure this time. On Friday, we'll know what it is. Unfortunately, they're set up to measuring organic materials that have 1,000 atoms per unit cell, so it takes a while. And so they put the sample in. So Friday, we'll know. We'll probably have the same structure that we've already heard today. Thank you.
Thank you, Jim. The next talk is by Professor John Mydosh, the Amsterdam-Leiden efforts towards a high-temperature superconductor. John?
Fine. Thank you, Brian. Let me begin by indicating the senior collaborators in this effort between Amsterdam and Leiden. We have Alois Manowski, who has diminished his efforts on the heavy fermion problem, and with a few students is growing some of the crystals and performing some simple measurements. With me here is Peter Kess, who is coordinating the efforts from the Kamerlingh-Onnes in Leiden, and we are also joined by a perovskite chemist, Dan Ido, in the chemistry department at Leiden. Due to the non-availability of the New York Times in Holland, we began our efforts rather late in January, and our first task was to reproduce some of the lanthanum strontium systems and showing some of the mandatory curves, which you've seen ad nauseum this evening. Nevertheless, we have in one of these particular systems, or in many of them, let me just pick out one which we want to go a bit further with. We have a rather sharp susceptibility transition and a nice plateau at low temperatures, this indicating a rather large Meissner effect, I think of order 40 or 50% of the sample. This is then further verified if we go over to resistivity data, which show similar sharp transitions, the resistivity going to 0 at approximately 32 degrees Kelvin, and a step further at this time in the beginning, I believe, of February, was to take this rather nice sample and to begin to look at magnetization loops, in particular below the transition temperature, and to work our way down. Now, at 30 degrees Kelvin, the hysteresis loop looks almost totally reversible. There may be a small irreversibility here, and this indicates that pinning effects and thus critical current in the field are very small. However, the situation becomes a little better as one goes down to lower temperatures, in particular at about 5 Kelvin. The hysteresis loop opens up, and this means there are more optimistic possibilities of having enough pinning to be able to use this material in practical applications. Just about at this time, we learned, this time through the New York Times, because one of us was in New York, that there was another phase of this system which was going at higher temperatures. And let me show you one of Minovsky's samples, which is the multi-phase system, which shows indeed a very sharp transition, approximately at 90 degrees. And showing the raw data, there's another, perhaps more interesting, or another anomaly occurring at about 240 degrees, a tiny dip, which has been found in a number of other samples of this particular mixed phase. The other two, I guess, triangles or other dips have not been very reproducible. We then went on a bit further for this sample to show that the resistivity blowing up became hysteretic upon cooling and heating. That there is, by cycling this, if you go through the cycle a number of times, this seems to be constant. There is a slight shift of about 3 or 4 degrees here in the resistivity, and also doing the susceptibility. Again, this is the mixed phase. The susceptibility similarly shows a hysteretic type behavior, which seems to persist all the way down to the low temperatures. In most of our studies, we have been including the imaginary part of the AC susceptibility, and that seems to be almost complementary to the real part, here in this case showing a bit of hysteresis again. Well, then our final efforts, which just have very recently begun, perhaps even they are still going on now at this time, since it is morning in Holland, or late morning. To summarize what has been happening this week, the green phase we tried to duplicate. I think it's not the proper green phase, but what we ran into here was antiferromagnetism and semiconducting behavior. We then went on to reproduce the 1, 2, 3 phase. We've been getting temperatures around 86 degrees. We haven't yet optimized the heat treatments to get higher temperatures. We did a 1, 2 strontium phase with copper 3 and varied it a little bit. This turned out to be an insulating phase. We then went on this week and we did a lutetium phase. The superconductivity appeared through its diamagnetism at about 90 degrees Kelvin, and we seem to be getting a very strange low temperature behavior. The plateaus, which I showed on the previous slides, appeared. However, as one went to lower temperatures, in particular below 15 degrees Kelvin, the susceptibility returned to 0, meaning the superconductivity disappeared as we pursued the temperature down to 4.2 degrees Kelvin. We have a gallium diluted sample which has no effect upon the superconductivity temperature. However, the comparison between a gadolinium and a lutetium of the same concentration seems to show that the net plateau susceptibility is larger in the lutetium, meaning perhaps that the gadolinium is contributing a paramagnetic component to this superconducting susceptibility, but in no sense influencing the TC. So this would be, I think, similar to other data reported this evening. Thank you.
Thank you, John. Next talk is microwave measurements on lanthanum strontium copper oxide by Professor S. Sridhar.
I shall try to describe some micro-absorption measurements in the lanthanum strontium copper oxide superconductor. This is the rather minuscule army that is marching on this problem. Since this measurement is unfamiliar to most people, let me just give you an example of a standard material like tin, on which I did some measurements some time ago, the kind of information one can get, what one measures is the surface resistance, which is proportional to the power absorbed in the microwave power absorbed by the superconductor. This is a plot for tin of log of RS versus reduced temperature, and covering orders of magnitude. The points are experiment. The dashed line, the line is BCS theory. The agreement is excellent. The point of is that if properly done, one can get orders of magnitude sensitivity and detailed information on scattering, and also about the local versus other more subtle aspects like local versus non-local electrodynamics. Conversely, data like this can be tested with models of superconductivity. For instance, in BCS, surface resistance is activated decreases exponentially at low temperatures, and also there are specific predictions for the surface resistance and penetration depth. Just for the record, we make our own samples, and they appear to be pretty good. We have also measured the susceptibility, and we see pretty much what other people see Curie-wise at high temperatures, and also the diamagnetism. Let me show you some measurements at 10 gigahertz on the surface resistance of lanthanum strontium copper oxide. I've normalized the data to 40 Kelvin. Also shown on this plot is the DC behavior on the red dotted line here. Now let me contrast this on the next plot with the measurements on tin again. This is now a logarithmic scale versus reduced temperature, whereas the previous one was on absolute temperature. And the standard BCS material measured in the same configuration looks like this, and the theoretical line just passes through the points. Now, overall, my first impression on this is that this lanthanum strontium copper oxide material looks pretty much like BCS. The deviations may be ascribable to the fact that the transition is actually broad over a couple of degrees at least, whereas tin is an extremely sharp, shows an extremely sharp transition. In addition, we see some steps here, which may be due to perhaps, I've heard of perhaps grain boundaries having slightly lower TCs. The point is that whereas the DC measurement shorts out when the first superconducting network forms, the microwave measurement is sensitive to the normal absorbing parts, and that kind of information comes out of this. Now, I'm trying to fit the experimental data to just taking the BCS form and putting a broad transition on it. I haven't done that yet. Let me just say that in more detail, the other thing that I'm planning to do is there's a background, unfortunately, which limits the measurements down to this temperature. Well, I'll try to reduce that over at least a couple of orders of magnitude. From such data, one can get the information about the temperature dependence of the gap, perhaps the nature of the pairing, and the density of states. One final comment is that this type of measurement is particularly attractive in these materials because other probes, like specific heat, are much harder to measure as far as their detailed temperature dependence goes because of the lattice background, whereas these are purely electronic. Thank you.
Thank you. Last but not least is Dr. John Cooper, who's going to talk about thermoelectric power measurements on some high-temperature superconductors.
Cheer up. So I'd like to present a small piece of work on the thermoelectric power of some high
TC superconducting oxides by George Gruner's group at UCLA, and all the samples except for 2 were made by Barakat Alavi. I have a transparency here about the thermal power, but I think I shouldn't try to explain it at this time in 5 minutes. But one reason why the thermal power is particularly interesting is that in some materials, for example in organic conductors, a large temperature-independent thermal power, a famous minus 60 microvolts per degree K, which you can obtain theoretically for a half-filled Hubbard subband, gives crucial evidence for the importance of Coulomb correlations. So one goal of our work was to see whether we could get systematic behavior of the thermoelectric power, and then to see whether this data fitted the so-called modified Hikes formula, where the log 2 represents the entropy of the electrons, and rho is the number of electrons per site. And this formula only holds in the limit of strong on-site Coulomb repulsion, and a bandwidth of the order of the temperature. Actually, it can be about 5 times the temperature. So this shows some experimental results on what we call the pure stuff. This is 2 independent preparations of lanthanum copper oxide. And you can see that the main thing is a temperature-independent large positive thermal power, indications of superconductivity, perhaps from the surface at high temperatures, 80 K, then falling nearly to 0. And then with very small amounts of barium, the thermal power really shoots down. I'll just show one curve. You've seen many this evening of thermal power versus temperature in the superconducting region. This is resistivity versus resistance versus temperature. And you've got a large positive, not very temperature-dependent thermal power in this so-called metallic state. So I'm jumping transparencies. This shows this shows every thermal power sample that we've measured at UCLA. I didn't leave any points off. I added this one so that I could say this. So this is a plot then for 3 different compositions of the room temperature thermoelectric power versus X, where X is determined from the weighed amounts of material. And the point I'm trying to make, this solid line is this theoretical formula where you say that you start off with 1 copper d electron per site, and as you add barium or strontium, you're gradually removing electrons from this 1 copper electron per site. And we think as a first approximation, this line, which doesn't contain any adjustable parameters, shows a reasonable description of our thermal power data up to about x equals 0.1. So in conclusion, the low concentration regime, pure material, thermal power is very large, T independent and positive. This is all above 80 K. Below 80 K there are traces of superconductivity. S is quickly reduced by doping. At room temperature, it seems to us that Sx, thermal power as a function of concentration, both in barium and strontium alloys, can be described by the Hikes formula, which follows from the Hubbard model in the large U limit. That means only 1 electron per site or less, with K T over W of the order of 0.1 or 2. Then for concentrations X bigger than 0.1, or 0.2 in some people's language, S remains hole-like and has opposite T dependence to a metal. Its magnitude is smaller, and it corresponds to a bandwidth about 1/10 that of copper, which is roughly consistent with susceptibility and specific heat data. I'd like, if I could, just to show one more transparency. Oh dear. Oh yeah, here it is. This just shows other work, recent work at UCLA on high-T superconductors. These people are here, so if you're interested in surface impedance in this frequency range, or the effect of impurities, nickel, cerium, or zinc in place of copper, or in other high TC materials, you should talk to them. Thank you.
Okay, we have perhaps time for a few questions. It's only 3, you know. Yes.
I'd like to comment on regarding to Holland data of re-entrant. I was in Illinois in January. I was observed similar phenomena in the lanthanum barium copper oxide as well in the entrant. I'm still puzzling myself. This whole system might be connected with the giant diamagnet, but of course in superconductivity occurred. So re-entrance cases sometimes very strange phenomena occur. So I'd like to make a footnote. So I'm still puzzling myself in the lanthanum barium copper oxide.
Yes.
My name is Sangbun Nam and Wright Patterson or Wright State University.
I'm Dennis Clardy from MIT, and I have a question for Dr. McHenry. I wanted to know if you look at the T sub C equation that you have, can you maximize that with respect to the parameters and obtain a ceiling on T sub C for all superconductors? And secondly, do you have the relevant molecular orbital plots for a d-delta bonding superconductor?
Yeah, I have both. I can tell you answer both questions. One, sir, let me put up a transparency. First of all, there is a limit on that expression for TC, and the upper limit coincidentally turns out to be about 240 degrees Kelvin. Just simply by taking first derivatives with respect to the two variables. But let me say that that formula has been around for 4 years, so well before any of this talk about 240 degrees. And yes, I do have a picture of what we think the orbital topology looks like at the Fermi level, and I expect that this will be a little bit controversial. This is what we see in several clusters as our highest occupied molecular orbital. And let me point out that there is significant copper character on this orbital, but I chose not to show it in this picture because it gets a little too busy. Let me describe, though, that the copper character is essentially anti-bonding with respect to the oxygens. And the important feature of the orbital is that there is a little bit of lanthanum character on it, and that lanthanum character is a very diffuse D character. And the most important feature of the orbital is the fact that the orbital shows p-pi bonding between oxygen atoms, and that p-pi bonding is out of phase on different. It's in phase along the 110 direction and out of phase across the lattice. And I should point out that this particular orbital doesn't break symmetry because it's a degenerate orbital. It's equally possible to have instead of the dxz, the dyz coupling the other directions.
Fred?
Yes, Fred Muller, Los Alamos National Laboratory. I have 2 questions for Professor Dr. John Mydosh. The first question is the following. When I first came, and a little bit of a commentary to this meeting, I thought the contribution perhaps of Los Alamos of making gadolinium superconductors through Zachary Fisk was going to be unique and interesting. And I think what this meeting has proved is that no one has a lock on the periodic table, and this is an international effort, and everyone is making great contributions, including, of course, the work at Leiden. Now, the reason I mention the work at Leiden in terms of gadolinium is the following. About 3 years ago, John Mydosh and I were having a conversation on the telephone, and one of the things we were discussing was an isotopic effect in gadolinium, and as far as I know, that sample of isotopically pure gadolinium is either at Leiden or was returned by myself to Joe Cable, and I don't know which. The point is the following. I think it would be fascinating to try and measure the isotope effect in gadolinium, and certainly Minovsky is one of the best people on the planet for doing that. And as far as I know, gadolinium is one of the easiest materials to make in the sense of getting reproducible high TCs. And so I would strongly urge or suggest or ask my colleague whether he would be interested or plans to do the isotope effect using that sample of gadolinium which came from the Oak Ridge National Laboratory and either is in his desk or perhaps, I hope not my desk, or is it with Joe Cable?
My answer is yes, Mr. Dr. Fred Muller.
Thank you very much. The second question is a little bit more apocryphal and has to do with the fact that, John, did you close down on the Americans without the aid of newspaper articles, either from Beijing or from the New York Times, because perhaps, like we did at Los Alamos, we brought in a lot of retirees and helped them come and return back to the laboratory. Did you press the shade of Camerlingonis to give you your help?
The answer to that is no, Mr. Dr. Fred Muller.
Thank you very much.
I don't know how we can follow that with anything better. So let me just say that I've never been in a meeting at 3 o'clock in the morning, so this must be truly an historic occasion. Also, I'd like to thank the audiovisual people for being here at 3 o'clock in the morning. And, well, let me first thank the speakers and the audience for their tenacity. We'll close this session. Thank you.
Thank you.